Good, uh, good morning and good afternoon or good evening, wherever you are, and welcome to the iCANX talks. And the purpose of the iCANX talks is to connect the world and the universe through science. Science has no national boundaries, and our purpose is to really promote science and scientists and also connect the world through science. So my name is Jagadish, and I'm a professor from the Australian National University, and I'll be serving as a moderator for this talk today. So we have been really featuring top scientists, and these are the 4 scientists in the March we are featuring. And then yes, last Friday, Professor Bob Langer has given a talk from MIT, and then today Professor Martin Green from University of New South Wales is going to give a talk. And then next week, we're going to have Professor Yasuko Arakawa from University of Tokyo is going to talk on quantum dots. And Professor last Friday of March, and we're going to have Professor Naomi Hallis from Rice University is going to talk about plasmonics and nanoparticles also. So we also have got young scientists, and then really they're acting like panel members and challenges for the speakers so that they'll be able to stimulate the panel discussion and then ask also some insightful and exciting questions. And then today we have Shanyuan Niu, Dr. Shanyuan Niu from Stanford University. And also we've got a special guest today, Dr. Zhengrong Shi. Of course, he's a famous scientist, and so from Shanghai University of Electric Power. And so he'll be participating in the panel discussion, and we warmly welcome all of our panelists and the speakers today. And then today, I think we've got a world-leading scientist and engineer in terms of Professor Martin Green, and then he doesn't need any introduction. He is a world-renowned scientist, and he has made pioneering contributions in the field of solar cells, and he has held world records in silicon solar cells for many years. And so as a brief introduction, in fact, Professor Martin Green has started his solar photovoltaics group in 1974 in the University of New South Wales. And then now, of course, is a world leading group and in this area, and then many students and postdocs have been trained by Professor Green and his colleagues. And then they've really done a pioneering work. And Professor Green has invented many aspects of solar cells, including buried contact solar cells in 1984, and then many of the industry solar cells are using this particular technology. And then he serves on many boards as well. And in the CSG Solar, he's the research director, and then he's demonstrated 25% efficient solar cells, and then he's done pioneering work in the field of 3rd generation solar cells. And he has won many global awards. And then in fact, the most recent and most exciting award is the 2021's Japan Prize. And this is really pioneering work. Particularly, Japan Prize is equivalent to a Nobel Prize for applied scientists. And most of the time, Nobel Prizes are given for fundamental sciences, but the applied sciences Japan Prize is seen as the equivalent to the Nobel Prize. He has won 2018 Global Energy Prize, and he has won the New South Wales Scientist of the Year in 2008, and the Millennium Award in 2000, and 1999 Australia Prize, and also Australian Academy of Sciences honored him with Ian Walk Medal and Fawzi Medal. And of course, I can go on and with his many long list of accomplishments, but he requested that I should really keep the introduction short so that he has got time to speak about his work on recent developments in solar cells and role in climate change mitigation. Martin, please go ahead. Thank you very much.
Thank you, Jagadish. I'll just share my screen. Okay, can you all see that? Oops, it's got away from me. I want to continue? Yes, I do. Okay, can you see my screen, Jagadish?
Yes, Martin, I can see part 1, big picture.
Okay, we're ready to go. Actually, I have to go back 1 or 2. We'll just get back to the start. I'm not sure why it jumped, but anyhow, we're back to the start. So I'm Martin Green, as Jagadish mentioned, from UNSW Sydney, And I would like to talk about things that have happened recently with solar cells and how solar cells have now positioned themselves that they're in a position to really impact greenhouse gas emissions and help mitigate some of the impact of climate change. I work in Sydney, and you can see a picture of Sydney below me there. The building in the centre there is where our research labs are located, and on the right, that's the Solar Industrial Research Facility at our university, where we work on transferring some of our technology to industry. So we have a pilot line there for fabricating the cells, and we test equipment from manufacturers and so on there as well. Okay, my talk is divided into 5 bits. So I've got 5 parts. But just to start with, I'd just like to give some of the big picture developments, an overview of some of the big picture developments that are occurring within photovoltaics. So the big thing that has happened, this is showing the price of a solar module, shown over there on the right. But the really big thing that's happened in the field is that the price of the modules has dropped incredibly dramatically over the last 12 years. And during the talk, I'll give some of the explanation for this. And Dr. Shi, who was mentioned in the introduction, had a big part in bringing these price reductions into effect. But in 2008, solar modules were selling for US $4 a watt. So the modules on the right might be about 300 watts rating. So back in 2008, they were selling for over $1,000 wholesale. But last year and this year, they're selling for under 20 cents a watt. So that's a factor of 24 times reduction in those 12 years. So really quite dramatic. It's hard to think of other commodities where the price has reduced so quickly. So a module like that now at the wholesale level would be selling for $60 or $70. So quite a dramatic change. And that's really changed quite dramatically the outlook for solar and what you can do with it. Since 2012, the cost reduction has been steadier than in the years between 2008 and 2012. And I plotted that shaded region here on a semi-logarithmic plot. So, you know, what I've plotted is the US dollars per watt of output of the module. But on this semi-logarithmic plot, you can fit it approximately by a straight line. I can't quite see it on my screen because I've got other people on there, but I'll get rid of them. Okay, I can see it now. You can see that on the semi-logarithmic plot, things are approximating a straight line reduction. So that means the costs are reducing exponentially. So that's like in microelectronics, you know, Moore's law is the number of transistors on a chip doubles every 2 years. So you're getting a similar type of things in photovoltaics. But what's been happening there is that the average selling price, so this is the wholesale price of the modules, is dropping by about 20% a year. So the blue shows the traditional technology used to make the cells, and the red shows a new technology that's been introduced over the last few years, and it's really having a big impact on the field that I'll talk a little bit about later. But I'm very proud of that technology because I actually invented it back in 1983. So it's my technology. But that's the PERC technology, which we'll get on to a little bit later. So these cost reductions, as I said, have just changed the complete output for solar. So the International Energy Agency, who's been quite conservative in earlier years in their projections for solar, have suddenly seen all this happening and have realized that solar is positioned to make a really big impact in the future. So in their most recent report, they say solar is now the cheapest source of electricity in most countries. So it's cheaper than coal, it's cheaper than nuclear, cheapest source of electricity in most countries. And it now offers some of the lowest cost electricity ever seen. And the really good thing that I'll be talking about a little bit later is that costs are still reducing. So even though we're already at costs that are amongst the lowest cost electricity ever seen, we're going to go lower. So we're going to go to electricity prices that one of my colleagues has described as insanely cheap electricity in the future. So this price reduction is increasing the amount of solar installed. So the graph on the left shows the cumulative solar installation in gigawatts. So 1 gigawatt is the output of a large coal or nuclear power plant. So at the end of 2020, there was 790 gigawatts of solar installed worldwide. So it's starting to be quite substantial in terms of the output. And on the right there is shown the wind output. So you can see if you look at the growth in the wind installation, you could fit the growth approximately by a straight line. So that's linear growth that you're seeing for the wind. But if you look at the solar, it's still shooting upwards. And that's because the amount that's getting added each year is increasing exponentially. So that we're still in a region of very rapid growth. So at the start of this period in 2010, a lot less solar installed than wind, but because of this exponential rather than linear growth, it's overtaken wind. And we can expect that to happen with other technologies as well. So solar, if it can continue this exponential growth, will overtake nuclear and coal and et cetera, et cetera. So it's expected by about 2040, 2050 type of era, most of our electricity could come from these solar cells. The amount installed in 2020 was 140 gigawatts is the sort of figure that people are settling on. If you go to the next highest unit, that's a terawatt. So that's about 0.14 of a terawatt or a seventh of a terawatt. So on the right there is plotted these annual additions. So for 2020, plotted the 140 gigawatt added on this graph here. So that's that point. You can see there at 2020. But if you go back in history and plot all the amounts that were installed each year up to then, you can see again on this semi-logarithmic plot, approximately a straight line. So that's showing exponential growth. But if you project the growth over recent years, you can see that you're going to get to this next level here, which is the terawatt level. Sometime over this decade is very likely if we can sustain the type of growths we've seen recently, or if we can go back to some of the growths earlier in the decade, we might even get to that level by the mid-2020s. So that 1 terawatt a year is very important because that's the level that you really need to make a very significant impact upon greenhouse gas emissions. So this chart here is from 2015, done by Global Carbon Tracker, but it plots the total CO2 emissions globally up to 2014. And then past 2014, it's projection of the type of trajectory that you're going to need to maintain a 2-degree temperature rise. And the thing that attracted me about this graph is it shows very clearly that we've got a big problem in that if you just look at the 4 biggest emitters, which are plotted here, despite their best efforts, like everyone is trying to reduce their greenhouse gas emissions or at least constrain them as much as they can. But if we look at that trajectory that we need to reach 2 degrees centigrade and you look at the projections of the 4 biggest users, you see there's a problem in that the whole budget of emissions is going to be used by those 4 alone. And there's still 160 odd countries that aren't included in that total. So when I first saw this, I was a little bit despondent. I said, how are we ever going to beat this? But then if you look at the impact of a terawatt of photovoltaics, if you install 1 terawatt a year, you get these little steps. So if you can install by the mid-2020s, if you can reach that 1 terawatt level that I talked about in that last graph, and displace the use of coal from electricity generation or oil from transport, this is about the amount of CO2 emissions that you save each year. So if you can do everything else to decrease emissions and then displace coal from electricity, oil from transport, and install 1 terawatt a year of photovoltaics, you can see you can generate pretty much the right trajectory to get on that 2-degree trajectory. So, that's been something new. Photovoltaics has now become so cheap that this is something that it's feasible to talk about happening. Oh, that's a bit of a big picture story. So what I'd like to do now is go a bit into the technology. How do they work? And, at the crux of all this was Albert Einstein, as in many areas of science. And so his Nobel Prize in 2021 was awarded for his explanation of the photoelectric effect. So when you shine light on generally high energy ultraviolet light onto metal, you can get electrons ejected from the metal. And there was something puzzling about that, in that if you shone red light, it didn't matter how intense it was, you didn't get any electrons injected, no matter how strong the intensity of the light was. Whereas if you shone blue light, even if it was very weak, you could get electrons injected. And that was a bit of a puzzle, because everyone knew that light was a wave, and it was just thought that it would excite atoms in the material, and electrons, pretty much depend on its intensity rather than anything else. But Einstein realized that one way of explaining that effect was to regard light as a particle in its interaction with matter. So its energy exchange with matter had to come in little packets, as if the light was coming as a steady stream of particles. So that was a groundbreaking innovation in thought, in that prior to then, it had been well established that light was a wave with Maxwell's equations and so on, and it all fitted together perfectly. But to explain this effect, he made that bold proposition, and turned out to be right. In its interaction with matter, light does act as a particle. So the little drawing up the top there on the right tries to capture both those aspects of light. It comes in a little packet of energy, which is represented by the finite extent of that symbol. And you can see a wavelength there. You can see something wiggling around, and that gives you an idea of the wavelength of the light. But the important thing that flowed from his idea was that the energy of these packets would depend upon the wavelength. So the shorter the wavelength, the more energy each packet had. So blue light had much more energy than red light in each packet, and that was the reason that you could get the photoelectric effect from it. So that bold proposition led to quantum mechanics, in that de Broglie postulated that you could say the same thing about an electron. Like in the previous drawing, electrons were drawn, shooting out like little particles, but de Broglie postulated that you could regard them as waves, sort of turning the argument on its head. And that sort of led to wave mechanics and quantum theory. By the 1930s, quantum theory was sufficiently developed that it was getting applied to real material problems. And Alan Wilson, a British scientist, applied it to understanding the properties of semiconductors. And he developed essentially the modern theory of semiconductors, which is what solar cells are made from, semiconductors. But the main idea coming from his work, that within a semiconductor, there were bands of energy that were allowed to electrons, separated by forbidden bands. So instead of a continuum of energy being available to electrons within a semiconductor material, it was partitioned up, so there was only certain energies that were allowed. So that explained a lot of the properties of the semiconductor. So this just gives a diagrammatic effect. So with the photoelectric effect, this is meant to represent the material with the electrons sort of clustered around the lowest energies available to them, shown as the shaded regions. And if you get an energetic photon, it excites one of these electrons to beyond the energy that it needs to escape from the material, represented by this vacuum level here, shown as the dotted line. So you're getting a photon ejecting an electron from the material. With a semiconductor, this is what happens in the solar cells. A lower energy, you can have a high energy electron do the same thing, a high energy photon do the same thing, excite an electron from these occupied states down here right out of the material, so you can get the photoelectric effect in the semiconductor. But if you have a lower energy photon, red and green and so on, even blue, you can excite an electron from one of these bands within the semiconductor material that's fully occupied by electrons to the next available band, which is has no electrons in it. So that's a really crucial point about a semiconductor property. So the minimum energy you need is given by what's called, oh no, I've gone back a few without meaning to. The minimum energy involved is the distance between these two bands, which is the band gap. So I'll talk a little bit about the band gap in the talk. So that's a very important property of the semiconductor, because that determines the energy of the photon you need to do that excitation, and hence the wavelength of light that the cell can respond to. If the photon has less energy than to cause this transition, you won't get the photoelectric effect. If it's got more, you will get it. Once the electron's excited, it sort of stays up in this conduction band for a finite amount of time. Like if this was a metal rather than a semiconductor, and you had an excitation, say the diagram on the left here, that wasn't enough to cause the electron to escape, it would very quickly relax back to the lower energy. But in a semiconductor, because of this band structure, this electron stays excited for a finite amount of time. And that's the time that you've got to work on it to extract energy from a solar cell. So that sort of delayed in the relaxation of the electron back to its ground state is important in a semiconductor. The other thing that is important is this band that was originally full of electrons. The excitation leaves a vacancy in that band, and like a bubble moves through water, this hole can move around in the valence band. So you can get electrical conduction of carriers by movement of this hole within the valence band, in the same way that the excited electron moving in this conduction band allows electricity to flow through the semiconductor. That's the other important point. So that's basically how a solar cell works. You think of the light falling on the solar cell. Sometimes you have to think of it a wave, in that you design anti-reflection coatings for the solar cell, and you have to think of the electron as the photon as a wave to design those correctly. But once it enters the material and interacts with the semiconductor material, you follow Einstein's initiative and regard it as a particle. And if the photon has sufficient energy, it creates this electron-hole pair by exciting an electron across the band gap. And then the other thing about a semiconductor is you can change its properties so that it either has what's called positive or p-type properties, which I think is the bottom region here, the green region, or negative or n-type properties, which is the top region. Or have I got it back to front? No, I've got it the right way around. So the blue region at the top is the negative or n-type region, and I'll explain how that's achieved shortly. But the holes can move easily through the p-type material, the positive type material, and the electrons can move easily through the n-type. So that causes a directional flow of the carriers. So the electrons move wherever they're generated. They move through this blue n-type region, around through whatever electrical load you connect between the connection to that n-type region to the connection to the p-type region, where they meet up with a hole and they neutralize each other there. So that, basically that's it. That's how a solar cell works. You needed Einstein's insights to have any chance of understanding it, together with this, what's called a p-n junction, which gives you the directional flow of the electron and holes within the material, and allows you to generate or pass current through any electrical load, and hence generate power within the load, causing this little lamp here to shine, for example. So I'll talk next about part 3. That's a little bit about the history of solar cells, and explain some more of the physics as I go along. But the first silicon p-n junction cell was made in the early 1940s by Russell Ohl at Bell Labs. So he was experimenting with what are called cat whisker diodes. So I've done a little sketch of one up the top here. So you have a slab of semiconductor, and you poke a pointed wire onto it. And these have a rectifying property in that they allow current to flow more easily in one direction than the other, so that if you pass current in one direction, it flows quite quickly through the wire and through the semiconductor. If you try to pass current in the other direction, you get a lot less current flowing. So this non-reciprocal response. And that was very important in radar. So this was, in the 1940s, and radar was evolving very rapidly. So they're looking for better diodes to work at very high frequencies. So because these diodes were so small, little pointed contact, very low capacitance associated with them, so they could respond very quickly. So that was why Russell was interested in these diodes. But he thought if I could get some really pure silicon, they might work better. So he had a batch of very pure silicon prepared as using a crucible as shown here, just melted some silicon down in a crucible and re-solidified it, and then cut some little segments out to do some of these experiments with. But to his surprise, when he shone a light on some of these little segments he cut out, he got a very high voltage across them. And that was a real surprise. But he identified that there must have been a barrier. The semiconductor must have had two different types of properties, and there must have been a barrier within the material. He called one side of the semiconductor P-type because that became positive voltage when he shone light on it, and the other N-type because that became negative. And he realized that there must be something different about the semiconductor properties in those regions. And it was the junction between those two different types of region that was causing the voltage to be generated. It was soon found, investigating what was giving this semiconductor different properties, that introducing trace quantities of what are called dopants within the material changed their properties. So you had the N-type material that conducts electrons easily, and the P-type that conducts holes easily. And by adding specific dopants, so if you add boron into silicon, you can conduct holes readily in the material. If you add phosphorus, you can conduct electrons quickly. So that was all sorted out a few years after that. And William Shockley won the Nobel Prize in 1956 for developing the theory of these PN junctions and a new transistor structure based on putting them two PN junctions very close together. So by the end of the 1940s, the understanding of these PN junctions had just about reached its modern level. So it only took less than 10 years to go from first discovery of a PN junction to a more or less complete understanding of their properties, with William Shockley providing that insight. So in a certain sense, the photovoltaic effect was responsible for the development of microelectronics, because these properties of semiconductors are used widely in microelectronics. But it was the photovoltaic effect that unearthed them. Photovoltaics then took a bit of a backstage as people got more interested in transistors and so on. But in 1954, in late 1953 actually, some of the technology that had been developed for transistors got applied to solar cells, and that resulted in a big jump in improvement in the ability to convert solar energy with solar cells. So prior to this, there had been solar cells from a range of materials, like dating back to the 1839 when the first photovoltaic effect was demonstrated. And since then, a number of materials had been identified as producing electricity when light shone on them. But it wasn't until 1931 that the operating principles could have possibly been understood, because the basic physics wasn't there to be able to do that. And then with the discovery of the PN junctions, the theory could explain just about everything that was happening. But with the development of semiconductor electronics, PN junction technology was developed further, and it became possible to fabricate a decent cell. Initially 4% efficient, which was a big jump on anything seen before, then 6% and so on. It was such a big development that it made front page news on the New York Times. So this is an April edition of the New York Times, and there you can see the little headline, "Vast Power of Sun by battery using sand ingredient, tapped by battery using sand ingredient. And, much excitement about this new invention that had been made at Bell Labs. And you can see the picture in the upper right there. There was a lot of excitement about what you might use this technology for. You might be able to use it to generate power for a family and put it to all kinds of good use. But back then, the semiconductor technology was in the early days, and everything was very expensive, and it was too expensive to use for those types of general applications. But there was one application that was well suited for, and that was in spacecraft. So just a few years after, in 1958, the first solar cells were used on a satellite, Vanguard 1, shown there. And they worked very well. Too good, in fact, in that they kept beeping. There's a little radio signal emitter that's powered by these cells, and it kept beeping far longer than people really wanted it to. Those cells work so well. But in 1961, there was a serious attempt to develop the cells to their full potential for communication satellites. So the first communication satellite, Telstar, went up in 1962 and beamed the first TV signals across the Pacific and so on. But there was a lot of work put in at Bell Labs again to develop a standardized cell design that could be relied on to perform well and with a high performance. And that was known as the conventional space cell when I joined the field in the 1970s. And you can see a 2 centimeter by 2 centimeter device there with a standard geometry and so on. So that was the standard for a decade. And then in the late 1960s, ComSat Laboratories was established in the US to improve satellite technology in general. But one of the technologies that were decided to improve was solar cells. And Joseph Lindmayer, shown there in the little photo, was given the job of trying to improve solar cell performance. And he did a good job. He introduced some of the technology that had been developed in microelectronics, in the interim. So integrated circuits were starting to take off and so on by this time. So photolithography had developed enormously, and there's a lot more understanding about dopants and so on within the semiconductor material. So having a fresh look with all the new technology was available, he made the first improvement in cell technology for about a decade with what was known as the violet cell. And then just a couple of years later, other researchers at ComSat Lab went one step further and applied, again, some of the technology that had been used in microelectronics for selective etching. So there was things called V-groove transistors that were popular at one stage, but some of that etching technology that etches different crystal planes in the silicon at different rates was applied to forming these pyramids on the surface of the solar cell. So the pyramids are defined by intersecting crystallographic planes. They have pretty much the same geometry as the pyramids at Giza, but are a lot smaller. So just covering the whole surface of the device. And that greatly reduces reflection from the top surface of the cell, in that light has two bounces before it gets reflected. It hits the side of a pyramid, then it's reflected downwards and so on. So a big jump in efficiency to 16 to 17% type efficiencies was demonstrated by these black cells. And that structure became very important because with a slight modification, using a screen printing approach to apply these metal contacts, like screen printing T-shirts, simple approach to apply these contacts rather than the more complex technology used in space cells, able to produce very rugged cell structure that replicated very similar efficiencies. That was known as the aluminium back surface field, and that was commercially dominant, from the 1970s right until about 2 or 3 years ago. So it had a long history of being the mainstay of solar cell production. In that same era, there was oil embargoes, and the US started Project Independence to try and wean themselves from their dependence upon foreign oil. And developing photovoltaics was one of the technologies that was selected for doing that. And other countries like Japan introduced the Sunshine Project, aiming at similar developments. But the flat plate solar array project was very well funded in the US, particularly in the Carter administration. But one lasting legacy of that has been the design of the solar panels. So what happened was a number of bulk purchases were made of solar panels, and the Jet Propulsion Laboratory, who helped put the man on the moon, so they had the management structures to allow them to manage a program like this. They gave feedback to the manufacturers on what was wrong with their modules, and by this approach managed to improve the module technology. By the end of this program in 1985, essentially modern module technology had been developed. And that's been very important for photovoltaics because their reliability is one of the things that have made them so successful. Now, that's about the time I got started, and that's me there in the photo with the very long, very black hair, but with my first PhD student, Bruce Godfrey. But we had very simple equipment back in those days, and we were measuring a solar cell, and what we were measuring is shown on the right there. So that shows the output curve of a solar cell. So on one axis is plotted the current and voltage on the other. So if you have this device short-circuited, so there's no voltage across it, you can't do that with most batteries, but with solar cells you can, without doing them any damage in most situations. You get the short-circuit current. And if you open-circuit it, so there's no current flowing from it, you get the open-circuit voltage. So there's zero power at both those bias points because the power is the product of current and voltage, and one of them is zero in both cases. So the maximum power occurs as you move along this curve towards maximum power point. That's shown where the dot is on this particular curve, and then it reduces again as you go towards the open circuit voltage. So you get maximum power around here. So you can express the power as a product of the open circuit voltage, the short circuit current, and what's called the fill factor. In this case, a very lousy one of about 0.6 or 60%. But if you can get this curve squarer, you might get a fill factor. It's possible to get them over 0.9 in some materials, but 0.8 is very good for a silicon cell rather than the 0.6 showing here. So that's what an output curve looks like, and each of these parameters tends to depend on different design features of the cell. So that's why the output's characterized in this way. So we did very well in terms of increasing that open circuit voltage. We didn't need very sophisticated equipment to measure this or to produce the devices producing it. But NASA had initiated a program to improve cell performance by improving the open circuit voltage. And although we weren't funded under it, we were competing against US groups that were, and did quite well, as you can see from this graph. We managed to substantially improve silicon cell output voltage over what had been done before with some unique structures. So as you can see from the previous slide, we were getting well ahead of other groups in terms of the voltage we were getting. So all we have to do is fix up the current output and the fill factor, and we could get a decent cell. So we put a lot of effort into improving those parameters, and this is the team that worked on doing that. And in 1983, we were rewarded with our first world record cell. So we took the 16 to 17% efficiency that had been demonstrated at ComSat laboratories up to 18% with the cell that you can see in the photo to the right. So the graph there on the right is just showing the historical development of silicon solar cell efficiency going back to Russell Ohl in the 1941 through the developments of the 1950s, the developments for the Telstar satellite, then ComSat laboratories, and then we took over and had a good run, as you can see here, for the next 3 decades. And the people in this group have gone on to do wonderful things. This is Ted Spitalek on the right, who was heavily involved in setting up a lot of the manufacturing facilities in China, some of the very first ones there, and Stuart Wenham right at the rear there, who played a big role in the development of Chinese manufacturing and the reduction of the costs that that I pointed to earlier. This is the structure we used. Our main secret weapon was employing oxides along the top surface of the cell to reduce the electronic activity of that top surface. So this is a technique that was well known in microelectronics at that stage, but some additional challenges in applying it to solar cells in that you couldn't have it too thick. So we even put it underneath the metal contact. So this was our particular contribution to the technology, this tunneling type of contact here. So it reduces the electronic activity of the metal to semiconductor interface that you'd get without it there. 1983 was a big year. Not only did we get that first world record, but I drew my first diagram of this PERC solar cell, which stands for passivated emitter and rear. So the emitter is just the top of the cell, and that's just a carryover from transistor technology. This is the emitter of a transistor, and if this were a transistor, and this is called the base, similarly transistor name and terminology. But passivated top and rear cell is really what it's being said there. So we realized that, though we'd fixed up the top to get our 18% efficient cell, we're going to have to fix up the rear of the cell at some stage, and this was just my idea as to what the best way of doing that would be. So using oxides again to passivate most of the rear and having small area contacts to the rear to reduce the detrimental activity of those rear contacts. So that's my actual drawing, as you might notice from the wobbly printing on it. We didn't have computers that could draw those for us back then. The other thing that we demonstrated reported in 1983, we actually demonstrated a year or so earlier, but the paper took a while to come out, was a tunneling contact based on polycrystalline silicon. So instead of using metal as a tunneling contact, as I showed in one of the earlier slides, to make the contact, we realized that polysilicon would be more robust in that it could withstand much higher subsequent processing temperatures than metal could, so you could produce a more robust device. So this technology has re-emerged over the last few years and has become of much recent interest. So it may be a technology that we see in production in the future. So both it and PERC are two technologies of commercial interest that we came across in 1983 and set a world record, at least outside our group, for voltage output with what's called a TOPCon approach. We were very close to 20% efficient at this stage, and that had been long regarded as a 4-minute mile of photovoltaics. So we pushed on and got our first 20% efficient result. This is the team grown a bit that achieved that result, and all have gone on to have a big impact on the industry, as I show here. So many past people from our group have impacted the subsequent industry. Our run of records was interrupted by Stanford University, who developed this unique cell structure where the light comes, I've actually shown it upside down here, light comes from this direction here, and all the contacts are on the rear. That's Dick Swanson in the image there, who was head of the group to develop that. That encouraged us to put the PERC cell into, to get it fully developed. So we re-established the world record quickly using the PERC cell and maintained it right through till 2014 using that structure, reaching 25% efficiency. So you can see the structure on the rear here that I'd sketched earlier. So since then, there's been further developments. Most of them have occurred in industry. So industry has taken over the running rather than the universities that had previously dominated this development of cell efficiency. So SunPower was a spin-off from Stanford University, and they took over where Stanford left off and got to 25% efficiency with their rear contact structure, shown the right way up here. So this is looking at the top. So it's very dark. There's no contacts on the top, all the contacts on the back, which look shiny as a consequence. And then Sharp, who subsequently became Panasonic, worked on this heterojunction structure called HIT or HJT, and it uses amorphous silicon with a lot of hydrogen in it, which effectively acts as a much wider band gap material than the crystalline silicon. But it was like some of the 3-5 technology that's used in transistors and so on, using heterojunction approach. They got to 24.7 with that approach there. And then by combining their approach with the Stanford University rear contact approach, we're able to beat our 25% mark with 25.6 in 2014. And then Canica, another Japanese company, pushed that up to 26.7 with a similar structure. And that remains the highest efficiency for a silicon cell, with a limit of about 29%, shown as the dotted line is the theoretical limit of how high you can go. When you look at what's happening commercially, however, that PERC structure that I invented way back in 1983 has taken over the market over the last few years. So in 2013, the beginning of this graph here, most of the technology is the blue and brown region, which was that aluminium back surface field technology that was developed back in 1974 that had dominated production, as you can see. But then you see little bits of yellow and grey creeping in and then growing very rapidly. So by 2020, the yellow and grey regions, a bit of the black is also PERC type technology, was accounting for 86% of production. So completely dominating the industry. So a very rapid transformation in the industry over that very short period. And I'll show some of the things that have happened as a result of that. I'd just like to talk very briefly now about how solar cells became so cheap. And Dr. Zhengrong Shi, as I mentioned before, played a big role in this. I think without his efforts, we wouldn't have the very cheap solar cells that we see today. Zhengrong was my 12th PhD student, but he decided he wanted to set up manufacturing in China around the year 2000. And in 2002, he opened his first factory, and this is the day of the opening shown in those photos there. So a bit of help of some of his colleagues that were also affiliated with UNSW, so Stuart Wenham, Ted Spidlak, and Fenming Zhang, are the three shown there, managed to set up a production line in China and very successfully developed the technology to a standard where it could be marketed internationally and so on. That was very important because when he started doing this, there was no commercial manufacturing of cells in China, and China was devoid of all the infrastructure you needed to do that competitively. So before Zhengrong did it, it was a fairly blank slate. But by doing so, he sort of opened the floodgates for other companies to develop quickly in China because his success was noted by some US investment banks who encouraged him to list on the New York Stock Exchange in 2005 and help finance him to be able to position him to do that listing. So there we are on ringing the bell on the New York Stock Exchange at the end of 2005. And that listing was very successful. It was reported as the biggest technology float worldwide of 2005, raising over $200 million with only a fraction of the company being listed. So Zhengrong was reported as overnight becoming the first solar billionaire and became very famous as a result of that. But again, there's three of us up there on the stage helping him ring the bell. But that was very important in that other companies noted what was happening and had seen how successful Zhengrong had been. So there was companies in China that were interested in manufacturing in China and repeating what Zhengrong had done. And there was US investment banks that had seen what the companies backing Zhengrong had done and wanted to do the same thing again. So this mutual interest prompted a lot of companies to list soon after. So you can see a few of them here. So within a year of Zhengrong listing, 2 other companies had listed, and then there was a flood of other companies with the only the global financial crisis in 2008 sort of slowed things down dramatically. But between Zhengrong's listing and that period, there were 10 companies. Each of these little waterfalls here represents one of them. But the 10 companies shown there managed to list. The they form the backbone of the present industry, those companies that follow the path that Zhengrong blazed. The ones that shown there with a little red sun, they remain in the top 10 of manufacturers in 2020. So 6 of the 10 have been successful. One of them wasn't really doing cells, so we won't really count it. So I guess 6 of the 9 were successful. 3 of the others have sort of fallen by the roadside, but success rate was quite high. The other thing, we were heavily involved with a lot of these companies in that our students, to be listing on the US exchange, the companies had to show contact to good technology, and that was demonstrated by recruiting people from our team, because Zhengrong was from our group and he had done well, so other people from our group would be hopefully equally as confident and able to help their companies in the same way. So 9 of the 10 companies had senior people from our team. Part 5, I've got 7 parts, so I've got a few minutes left, so I'll move quickly through the final 2. But how cheap can solar cells become? Here's an interesting question, because already the International Energy Agency says they're producing some of the lowest cost electricity ever seen, and there's still a long way to go in cost reduction, is my belief. So the PERC cell, which I said has just come on the market in the last few years, as you saw in that earlier graph, has really opened the floodgates of creativity, in that it's allowed a lot of things to be done cheaply that weren't possible in the past. So one of the things is it enables bifacial response. So it turns out to make it's just as cheap to make a solar cell that responds to light coming from either direction with the PERC technology. So you can make a solar panel that will respond to light falling on the front surface and the back surface. So you might say, well, why is that any use? But there's a lot of light that gets scattered onto the rear. So somewhere between, you can get somewhere between a 5 and 20% boost in output, depending on how careful you are to try and steer the light coming from the rear of the panel onto the panel. And, that's worth having, particularly when it's for free. So that's something that the PERC has enabled, this bifacial response at low cost. So that's contributing to recent cost reductions. The first commercial sales of the PERC cell was actually by our team. We used to sell cells for solar car racing. So this is the Honda Dream that won the 1996 World Solar Challenge. It used PERC cells, but we cut them in half to improve their power output. And that's what manufacturers are now doing with the PERC technology. So at the same time that it was introduced, the manufacturers started cutting the cells into half, so that instead of the square cells you saw in some of the earlier photos, they're now rectangular, as you see in these modules. And that just improves the power output you can get from the module. And there's some other benefits like shadow tolerance and things like that as well. And the other thing we did on that car was shingle the cells to prevent wasted space between the cells that you get in conventional modules. So overlapping the cells, as indicated in this diagram here. So some manufacturers have followed the shingling approach, and others, the shingling by some manufacturers has prompted others to look at what other ways of squeezing the cells closer together. And this is an approach adopted by LONGi, where they squish the interconnect down so it's very thin, and they can reduce the distance between the cells as a consequence. The other thing that's happened, because you can cut the cells in half, the cells about 6-inch square or 156 millimeter square were introduced about 2010, and they were dominant right up to 2019. Everyone stuck with that one size because that generates about 10 amps of electricity. The short circuit current is 10 amps. And handling any more current than that is very difficult. You need very thick conductors to handle it without resistive losses. But if you start cutting the cells into halves or even thirds, you can think about bigger wafers, because you halve the current output if you cut them in half. So that prompted a burst of creative thinking in terms of going to bigger wafers. So the biggest one people are using at the moment is 210 millimeters. So we had this big jump from 156 to 210 over a couple of years, coinciding with the introduction of PERC. that just gives you a better idea of the size difference. So this wafer here is designed for cutting into 3 bits actually. So you don't have to stick with cutting it into halves if you don't want to. So this graph here just shows the size of wafers used in microelectronics, the timeline along here. So for a long time, solar sort of lagged behind, and the wafers used in solar were a lot smaller than those used in microelectronics. But with this recent burst of activity, this is a compressed timeline in this period here, we've now caught up to microelectronics, and we're now using the biggest sort of squarish wafer you can cut out of a 300 millimeter diameter wafer. So microelectronics had this roadmap for improving wafer size. So this is a cartoon, I guess you'd call it, from around 2000 or so, when the industry had just adopted the 300 millimeter wafers. And they were anticipating by 2012 you'd go to 450, and by 2019 you'd go to 675 wafers, which is getting quite big. So you can make 450 wafers. I think this one was made around 2012. This circuit's on it. Though no trouble making it. The challenge has been doing the lithography that you require of these large areas, these nanometer resolution of these large areas, doing that economically. So that's been the real challenge, and the industry has stuck with the 300 millimeter much longer than was anticipated. So the transition to the 450 is now expected in microelectronics in 2029. But I'm just wondering, since photovoltaics doesn't have the same problem with photolithography, you know, whether the photovoltaics industry might now jump ahead of microelectronics and go to bigger wafers quickly. Bigger wafers need bigger modules that are growing very quickly, as shown here. This is the biggest I've seen, which generates 800 watts, shown at a trade show last year. So, you know, a few years ago, 300 watts was a big module, and now they're growing quickly. Mainly limited at the moment by the weight that 2 people can handle conveniently. So, you know, 20 kilos a person is a fairly reasonable load to expect them to lift. So 40 kilos is sort of the limit on the weight at the moment. But if you introduce mechanical handling, you could go very much bigger. So this is a 6 square meter module that using a different technology, and with machine handling, you might be able to go to much bigger modules. In fact, some have suggested that you might go to a module that the biggest that you could fit into a 40-foot trailer. So that's about a 30 square meter module. So this interest in big modules might stimulate some thinking about going to even bigger modules, you know, as big as you could fit into a 40-foot trailer and cart around the countryside. Going back to costs, there's the cost of the module, that's in dollars per watt. The other cost that is important is how much you pay for the electricity produced, which is usually expressed in dollars per megawatt hour if you're talking about large amounts of electricity. So this just shows the trajectory of solar over the last decade or so. So, you know, back a decade ago, it was quite expensive to install, much more expensive than some of these more traditional technologies that are shown here. But this red line shows the trajectory over this period, where it's moved through the field from being expensive to being very inexpensive. And this was, you know, what's happened that was picked up in the International Energy Agency report. So now it's become some of the cheapest electricity, as I mentioned. So this represents bids, companies bid for supplying electricity to countries or cities or other companies, and they guarantee these prices for a fixed period. And the other points there show, you know, the more conventional technologies, what the competitive prices have been. So it's only wind that has been able to demonstrate prices in these power purchase agreements, anything like solar. So how low it can go? So something like 0.5 cent per kilowatt hour. In Sydney, I pay 50 Australian cents a kilowatt hour for electricity, about 40 US cents. So this is a lot less expensive than I'd pay for my electricity here in Sydney, incredibly cheap. So what comes after PERC? I think tandem cells are the answer. So stacking cells from different materials on top of silicon. So you can take the efficiency from 25% to over 40% by doing that. So this is what our team is working on now, trying to develop other technologies that you can deposit onto silicon as a thin film that have a different band gap from silicon, a higher band gap from silicon. So with 2 cells, you can get a boost in efficiency and a bigger boost if you go to 3 cells. So 3 cells with different band gaps. Different materials are being explored. You really want a material that's abundant, non-toxic, stable, and efficient. And these little marks here show all the contenders, but none of them have 4 ticks at the moment. So we're still looking for an ideal material. Some of them are highly fancied, but haven't filled all those criteria as of yet. So that seems like a logical development of the industry, is to stack up to 2 cells onto silicon. But each time you stack a cell onto silicon, the idea is that you share the photons between the cells. So the top cells use the higher energy photons. The silicon cells use the lower energy ones because the band gap of silicon is well suited for red and infrared light, but not blue light. The amount of energy generated by the silicon cell reduces as you stack each cell onto it. So with 3 cells, the energy generated by the silicon cell is reduced to 1/3. So once you go to 4 cells in the stack, you probably don't really need the silicon. So you would have developed these thin film materials that you stack onto silicon. So I think an all thin film technology is the future. So can solar power the world? I'll have to skip over this bit because my time is nearly up. But this just shows the main CO2 emissions. So electricity generation is the main source of global CO2 emissions. So electricity only accounts for about 3% of global gross domestic product, GDP. So financially, it's not all that important. But in terms of greenhouse gas emission, just completely swamps the rest. So something that's an obvious target for reducing global emissions, and that's where solar is very well suited to overcoming. I won't have time to go through these, but this is just a scenario that plots through to 2050, just a transition where you transition from a world dependent largely on fossil fuels to one dependent mainly on photovoltaics, the yellow and brown regions there, and wind, the blue regions. Wind is quite complementary to solar. This is just showing end of last month from South Australia, their total electricity generation in that state. So the daytime, which are the light regions here, you can see the solar does the job. The wind tends to be lower. You know, you can see on this day here, or particularly this day, not getting much wind. But at night time, you can, generally get a lot more wind. So there's this day-night difference between solar and wind. And then if you look at the case of Germany, you get this seasonal difference. So you get a lot of wind, the green regions here in winter in Germany, not much in summer, just the opposite in solar. So wind and solar are a very good complementary mix. I won't go into this, but storage is very important, and pumped hydro storage is the way the grid uses to store electricity now, cheapest way of doing it and well suited for photovoltaics. Japan has a lot of pumped hydro storage, but it's mainly for their nuclear reactors, which I won't go into now, but this just shows the way that pumped hydro in Japan was installed at the same time and at the same rate as nuclear reactors. So each nuclear reactor is pumped up by a storage system of half the capacity of the nuclear plant. So storage in the grid is quite common and well developed. Another Australian group at Australian National University has looked for suitable off-river pumped hydro sites around the world and found over 600,000 sites shown here where it's suitable for putting a reservoir at the bottom of the hill and at the top. Very suitable for off-river pumped hydro that has some advantages. Batteries, of course, are the other technology of interest. And for some of the more demanding loads, hydrogen is the fuel of the future, many believe. And just this report recently of the steel mill being used to produce steel with hydrogen. So that's the end of the talk. A couple of points I wanted to make. Solar is already cheap, become cheap over the last decade, going to become cheaper over the next, insanely cheap. the PERC technology, I'm proud to say, as the inventor of it, continues to accelerate the pace of change. We're going to see 10 cents a watt module within the next few years, certainly over the next decade, and electricity prices of 1 cent a kilowatt hour and below. As shown on that chart there, if we can get up to this terawatt a year quickly, so sometime over this coming decade, solar can play a major role in mitigating global warming. So thanks very much for your attention. That's the end of my talk.
Thank you very much, Martin, for that such a fascinating talk covering a broad history to really various technologies and then your own contributions and then the future developments of the technology. And we've received many questions from the audience, but we'll limit our questions to 3 of them to really due to limited time. And then the first question is from Lee from Hong Kong University. Thanks, Professor Martin Green. I'm working in the materials science. Can you comment on non-silicon materials for future solar cell technology?
Yes, so I think it's very important to be working on other materials because I skipped over it a bit at the end, but I think there's an obvious extension of silicon technology is to go to a stacked cell on silicon. And for that, you need a cell made from a different material. So there's many candidates, so like I showed them very briefly there, there's about 6 or 7 candidates people are working on, but none of them have ticked all the boxes. So silicon is an ideal material for photovoltaics in that it's abundant, non-toxic, it's stable, and it gives you good efficiency. But finding another material with all those properties is very difficult. So perovskites is a very hot favorite. Like if you read Nature or Science, you'd think that perovskites were about to take over the solar world in terms of manufacturing and so on, but it's actually a long way from that. But it has a problem of not being very stable. It gives you the efficiency. It's not very stable. It's its main problem at the moment. But also it involves a lot of lead, which is not ideal for a technology that is going to be deployed in such huge quantities of solar. So other materials are important, but I'd encourage you to try and tick all 4 boxes when you're looking for materials for photovoltaics, particularly if you can do band gaps that are suitable for stacking onto silicon. That provides a ready market entry for the technology. So if you can't tap into the mainstream market, you're going to be limited to specialized applications with any competing technology. Tap into the main market. I think you have to link up with silicon the way the industry has grown. Thanks for the question.
Okay, thank you, Martin. And the next question is from Shi Hong at Solar Company. So proud to see you and Dr. Shi on the same stage again. Can you give your perspective on PV industries and business?
Yes, well, the industry's been very successful, and particularly in China. And I think Dr. Shi has been largely responsible for that in showing the way to a number of other Chinese companies. But at the beginning, companies like Zhengrong's were very small companies, and they've now grown to be very large companies, but they've learned a lot along the way. So the sophistication of the manufacturing is evolving year by year. The company's already very sophisticated, but breaking ground every year on improving the technology, improving methods for testing for the durability of modules and so on, which is obviously very important. And one reason for the photovoltaics success has been that the product has proved very durable in the field, but you've got to maintain that with new product you introduce. The industry tends to be concentrated in China, again, thanks largely to Zhengrong. Zhengrong was keen to integrate the whole supply chain into China because he realized that would reduce his manufacturing costs, the more of the activity that could be done in China. So the whole supply chain is being steadily back integrated into China. So very difficult for China to be displaced as a leading manufacturer at present. So as the technology evolves, there may be other opportunities because shipping sheets of glass around the world probably doesn't make a lot of sense. So other countries may be suited for manufacturing, the panels themselves with the cells made in China or something like that. So you may see more of a partitioning of the manufacturing as the industry evolves. Thanks again for the question.
Thank you, Martin. The third question is, thanks, Martin, for your wonderful talk. This is Xinhua from Ningxia at the west of China, a place of solar factory. We benefit a lot. Is that possible for solar cell be the major electricity power in the future?
Yes, I think very definitely. So I had to rush through the last bit because I was getting up to the hour that I was told I had for the talk, and I wanted to finish within that hour. I think to address climate change, we have to depend on solar as our major source, not only of electricity generation, but of primary energy generation. So one of the graphs I went through very quickly there was showing primary energy generation being dominated by photovoltaics. So that is a method for cleaning up our energy industries, so getting rid of fossil fuels from our energy industries. So for electricity, it's, by electrifying a lot of our industries, that is going to help. And electricity is easy to do with photovoltaics in combination with wind and storage, both probably battery storage and, pumped hydro is another possibility. Batteries technology is more similar to photovoltaics in that the batteries can be made and deployed quickly and everything, whereas pumped hydro is more of a traditional technology with long lead times and so on. But the big hope is on hydrogen generated from solar. So I think with these insanely cheap costs that we're going to see from solar, so already the International Energy Agency is saying we're producing some of the lowest cost of electricity ever seen, but that's only going to go down. So we're going to get to costs that have been unthought of before. So, electrolysis to produce hydrogen may well become economically feasible over the coming decade. So that gives you a fuel, more like the conventional fossil fuels for, powering industry and aircraft and so on, and for providing long-term storage within the electricity network, say from summer to winter in Europe, for example, where you have big differences in loads and so on between those times of the year. So so I think we probably need solar, like looking at the technologies that are going to be available within the timescale we have to address climate change. I think the next decade is very critical. So solar is really the only one ready to go in combination with wind to get to the scale that we need at the costs we need to displace fossil fuels quickly. And it's really important that we do that quickly. The quicker we can get started on that, the better. The good news is the industry is expected to grow rapidly over the next few years. So there's a bit of a backlog in supply at the moment, and that pent-up demand, although last year was a record year in the amount of solar produced, there's a lot of pent-up demand that we're going to see taken up over the next 2 years. So there'll be record years for the next 2 years in terms of the amount of solar installed. Thank you.
Okay, thank you very much, Martin. And I think we'll move towards the panel discussion now. And thanks again for your wonderful talk and then answering the wonderful questions very nicely. And so now let me share the screen and then share with you our panel members. And then, of course, we warmly welcome Dr. Zhengrong Shi. And of course, after Professor Martin Green's talk, he doesn't need any introduction. And after doing his bachelor's degree in Shanyuan University of Science and Technology, he has gone to University of New South Wales and did his PhD and became an Australian citizen, and then came back to China and then started the Suntech Power. And then, of course, as Professor Martin Green has mentioned, he has really transformed the industry. And not only he is a wonderful businessman and scientist, and also he is also a wonderful philanthropist. He has really supported and then many causes, including supporting the University of New South Wales universities as well. And so really, it's a pleasure to welcome Dr. Zhengrong Shi. And then I also understand that he's working on his new company now, and hopefully he will share some of the information about what are his current interests and other things. Please join me in welcoming Dr. Zhengrong Shi. Our challenger is Dr. Shanyuan Niu, and from Stanford University. Dr. Niu has done his bachelor's degree from the Nanjing University and then gone off and did his PhD from the University of Southern California. He is now working as a postdoctoral fellow, and he's really a rising star in the field, and he's published in advanced, the Nature Photonics and the Nature Communications and Advanced Materials and all some of the top journals or so. We would like to warmly welcome all of our panel members. So with that, now maybe let me start off with our discussion. And so maybe let me start with my first question. And then Martin, maybe I will ask this question, that what do you think of these third generation solar cells? People have been working on quantum dots and the hot electron solar cells and multi-exciton solar cells and other things. And what's your view in the long-term point of view? Though there was lots of exciting physics, but I haven't seen any significant enhancement in the efficiencies. Would you like to comment on that?
Yes, so I was actually director of a Center for Third Generation Photovoltaics. That's how the terminology got introduced into photovoltaics, I believe. But the only technology that I believe will be ready on the type of timescale that it needs to make an impact on global warming is probably the tandem cell that I briefly mentioned. So that by stacking other material on top of silicon, you can get this this boost in performance, which is quite substantial. So I think you can at least double the efficiency of the present modules. So many manufacturers now are offering modules in the 21 to 22% efficiency range, but I think a module efficiency of over 40% will be feasible with a tandem cell structure commercially, in the long run, maybe by 2050 or something like that. But, other technologies such as the hot carrier cell, I find very appealing, but just there's been little progress in actually demonstrating convincing experimental results with approaches like that. So it's a little bit like nuclear fusion. It's something that is very tempting, but way out there in the future, indefinitely. So I believe, we have to start working. We have to have technologies that can be implemented over the next decade or so for them to have any significant impact on greenhouse gas emissions. That's the really critical time. And I think the tandem is the one that we have to concentrate on. And even with it, finding a perfect combination of materials for that has eluded us so far. So I think that's a really important research area, finding a material that has all those four attributes I mentioned before. So some of them have three and some of them have two, but none of them have the whole four apart from silicon.
Okay. You. And maybe I'll ask our challenger, Dr. Niu, whether he would like to ask a question. And so please, Dr. Niu.
Thanks, Professor Jagadish. So thanks, Martin, for such an informative and inspiring talk. So I'm a material scientist by training, so I want to start with the materials-related question. So you briefly talked about the idea of tandem cell, how we can further increase the silicon cell efficiency by stacking materials on top of the silicon. So could you elaborate a little bit more on the materials of choice, and what are the major challenges you're facing with now?
Yes, so I think the hot favorite, if you took a vote amongst those working on photovoltaics, would be perovskites at the moment, which is a particular type of perovskite, not the mineral type, but a lead halide perovskite, for those that may not have heard of those cells. But they have done some quite impressive things in terms of efficiency improvement. So, the first perovskite cell was probably only reported in 2009 or so, but by this year they're already up to 25.5% efficiency. So, that's just unheard of in photovoltaics, being able to go from nothing to 25% over such a short period. But the big problem with the perovskites tend to be the stability. That is really a crucial problem to fix. So I've been doing a bit of a survey of field data that's come in on perovskites, but from the published data, it seems like you're getting quite serious degradation over periods of weeks rather than months or years. So the last 3 reports I've seen have reported, like 20% degradation over 20 days, something like this. There's many companies talking about commercializing, so maybe some of those companies are doing better, but certainly out there in the literature, and there's an enormous literature on perovskites, so it's not like the literature is only very small. But out there in the literature, anyone who has attempted outdoor testing of the perovskites has reported quite limited durability. So 20% degradation, which is the normal criteria for failing for a photovoltaic module, is 20% degradation, and that occurs after 25 or 30 years with a standard silicon module. So all manufacturers will warrant something like that. With the perovskites, you're talking, like 2 months would be a very good result for a panel that was reasonably efficient. Of course, if you make a very bad device that already has a lot of degradation built into it, you can probably make it last a lot longer. But if you make a really state-of-the-art device, you're stuck with rapid degradation. So it's orders of magnitude improvement that are required. And then you have the problem of the lead within the material. So in most countries, even in the European Union that has strict restrictions on hazardous substances, photovoltaics has a special exemption. So having lead wouldn't be a killer, excuse the pun, at the moment in Europe for a photovoltaic product. But someday that exemption is periodically reviewed, so that if they're at some stage in the future, countries could legislate to make photovoltaic product containing lead illegal. So it's a bit risky putting your money on a technology that has toxic material as a large constituent of it. So that's probably the favorite. Then there's other materials like copper, zinc, tin, sulfide. There's these materials that are sort of synthetic silicon. So silicon has a valence of 4 that gives it its particular semiconductor properties, but there's a whole group of semiconductors that you can combine different elements from the periodic table in the right proportions to get an average valence of 4 for the atoms involved. So CZTS, copper, zinc, tin, sulfide, is one that has 3 ticks. It involves abundant, non-toxic, stable materials, but getting the efficiency to a reasonable level is a problem. My team holds the record of 11% efficiency for the CZTS, but to be worth stacking onto silicon, you need an efficiency of at least 20%. So still got a long way to go with the efficiency. And then there's a lot of less developed materials that people are interested in as well. And organic semiconductors have had a big surge in improvement, over the last 3 years or so. So that previously they were too inefficient to think about in terms of stacking onto silicon, but now there's people talking about 18% efficiencies and so on. So getting close to that 20% level that you need to stack onto silicon, and you've got the abundance and non-toxicity, properly under control there. So stability is another issue with those, but they're becoming more interesting for tandems than they were just a few years ago. And there's a host of other materials people are working on, but none tick all 4 boxes.
I see. So it seems like still we've got a lot of work to do. All right.
Yeah, so I think it's a very important area too. So finding other materials, like initially, I think market entry, for consumer products, you can make a consumer product with organic photovoltaics, for example. So there is a small niche markets for some of these other solid cell technologies, but to hit the big time, to hit the main power market, I think you have to initially combine with silicon in this tandem approach to get your thin film technology exposure on the market.
I totally agree with you. Yeah, I totally agree because the boost in the efficiency is going to scale down the installation cost of other parts, which is essentially the major part of installation. So it can further bring down the price of like a residential system per se. So you mentioned about the degradation of the solar cells. So that like a that leads us to my hi.
Can you give us some chance? Yeah.
Sure.
Okay.
So
Okay. Good.
okay. Yeah. I
Okay,
think
now,
I'm waiting here for a little bit longer time.
Okay,
Yeah,
Dr. Shi. Dr. Shi,
Yeah, Dr.
and
Shi,
sorry that we kept you waiting for a long time, and so we just wanted to give the young person an opportunity to really ask a question as well. So, Dr. Shi, you have really transformed the photovoltaics industry, and of course, you are known as a Sun King, and you've started Suntech Power, and now you understand you've started a new company. I think I understand its new name is Sun Man or something like that. And can you just tell us about what you're doing in the new company and what's how you're translating your past experience of starting Suntech Power to the new one, and what do you see as the future of the opportunities for the photovoltaics industry?
Yes, and just as Martin mentioned, now solar become the cheapest source of electricity generation. So, and also as another important point, Martin brought up is actually we don't have much time. We have to focus on silicon, to tackle this climate change issue. So then, like now, if we look at deployment of solar, mainly is through solar farm, and there's also some commercial rooftops and so on. But really, there are many other applications, right? Scenarios, and for example, in the building integrated PV, and also now like all the vehicles is becoming electric powered, right? So we're talking vehicle integrated PV, and also communication like for 5G, mobile power, hydrogen generation, and so on. So in summary, it's like a PV plus is actually the entirely new scenario of PV deployment. So if we look at these conventional PV panels in piece of glass, I often describe the conventional panel as a blue piece of glass. So it's a big piece of glass and bulky, heavy, especially as Martin mentioned earlier. Now the industry tends to go into big modules, like a 40 kilogram per person, can carry. I mean, if you make it like a kilowatt or 2 kilowatt module size, it's a bit tough, for human to carry. So some as a new company, which I founded about 5 years ago, was try to change the module structure. So basically just try to get rid of glass and to replace a piece of glass with polymer composite material. So of course, many people tried that before. So and not so successful. I was actually quite bold to try again, because for the reasons, I mean, the whole industry has changed. Now the solar panel becomes so cheap, and then people will start to think more scenarios of applications. And secondly, I mean, sometimes you require resistance, and persistence. Sorry. So, and actually, the experience with some was a bit like that because now we have reference, okay, crystalline silicon glass panel. So any new products you try to introduce to the market, people will always compare to glass crystalline silicon solar panels in terms of power generation, power output, durability, micro cracks, aging, and so on and so on. So I think it really takes a bit time to educate the market and the customers. But so far, I believe we have done the job successfully so far. So, and more people now believe, this lightweight polymer composite material solar modules could be as sustainable, as durable as glass panels. So I think with more like deployment and more time of the data from the field, so I think more and more customer will come to this new technology. Yeah.
Okay. Thank you. So, Dr. Shi, again to you another question that many of the young students end up finishing their PhD, they become a postdoctoral fellow, and then they become an academic somewhere. But you've chosen an unconventional path of finishing your PhD, going and starting company. What advice you would give to the young people in terms of what are the challenges in terms of starting companies, and what do you expect? What skills they will be needing in order to be able to start a company? And then any advice you want to give to the next generation, please?
Sure. I think I only can share from my personal perspective. And when I started Suntech, I only had I just had a passion, had a dream. Okay, very bold passion, and and actually I prepared to be failure, honestly speaking. And but again, at the time, I was very confident. I mean, if the company didn't do well, there's no problem for me get another good job. So I think because so many years training, in Martin Professor Green's guidance. So and but once you started, then you really have to consider and look at, especially now, from my point of view, I mean, especially for intellectuals with PhD, we need to consider, do we have any unique innovation, right, about what we're going to do? I mean, any company, if you want to form a company, you basically try to solve the problem in the society, or provide a better solution for the society. So I think that is important. So after that, of course, there's a lot of operational issue you need to consider. There's a talent issue, there's a market, there's a capital, there's a supply chain, and also cost control, operational efficiency, and so on and so on. So if we want to commercialize the product, there's also a reliability issue, the quality control, so the management system. I mean, really a lot to do. But I think for intellectuals like us, if you want to get into business, we need to be really open-minded and to build a team, to know our strengths and weakness. Then you can build a team to try to strengthen our weakness. I think all these are very, very important. But again, very important to try to always get money ahead of time. So if you don't have capital, then it's going to be very tough.
Okay, thank you.
Okay, Jagdish, maybe I can ask the questions to follow up.
Please, please go ahead.
I think adding to that, one especially essential quality is never give up. I think all these, kind of famous persons, was always feeling the difficulties, and they never give up. Yeah, like Dr. Shi said that even he prepared to fail, he got, such things done. And then even he met some failures, he stand up again. I think that's a special, kind of qualities for the persons. So Martin, I have a question for you here is, you nursing, a big family for the solar cell, many students, and even they be professors or they be the entrepreneurs. Yeah, so very successful. Yourself are very successful professor, and you're nursing such a big family. All the people was grow up so well. So did you have any special recipe here or secret you can share with us?
Oh, I think the fact that we had a large group of very competent people within the group has been a very big factor. So I showed you some photos of the group growing. Initially there's just a few of us and then a few more, but all my students have been able to interact with a group of other talented people. So I think that creating that critical mass of talented people and creating that interaction has been important. And I've always tried to find research for my students that suits their ability. So no good sticking someone that's no good on theory on a theoretical problem or vice versa. So, so just finding the right type of project for each person, I think, has been another important feature of what I've tried to do when I've been supervising different students. But just having that vibrant research environment, I think, has been an important factor in the success of a lot of my students.
Thank you very much. So, Dr. Shi, did you have any, kind of story to share with us? How Martin, training you to be so confident?
Yeah, I think yes, Martin is really my mentor and friend, and for so many years. And I remember very clearly when Martin supervised me, as a student, he always gave a lot of room, for you to think, because I think probably there are different type of style of supervision, but Martin is the type he just give you some guidance and give you try to encourage you to think and have your own initiative in many ways. I just find that's very important. Actually, I inherit many of this this style in my own management. So like I guess if we want to manage a large group of intellectuals, you tend to be that give people more space to think, to play.
Okay, yeah. Now you take a position in Shanghai, right? Yeah,
Yes.
as in university, you are professor.
Professor in Shanghai University of Electric Power. They focused on electricity energy as as their major applications. Yeah.
So I hope you train your students in this way and get many, Dr. Shi come out. In Zhengrong's family, you have another group of, the big students come out.
Yes, thank you.
Counting on that. So, Jagdish, maybe we give the last chance to Dr. Niu, our challengers, to ask the last question, very last. Okay.
Yeah, please go ahead, Dr. Niu.
All right, sure, thank you. So since this is the last chance, I'll use this opportunity to seek some advice for like junior researchers like me, and including I'm guessing a lot of the audience as well. So more than often, I ask myself this question. So if I had the resources and freedom to work on any problem I want to work on, what would that problem be? So Dr. Martin Green, I want to get your opinion on that. Maybe except for the tandem problem you are working on now.
That was going to be my answer. So
I knew that.
I think that's one of the most important problems that a university research team can tackle, because we're so far from having a solution there. I believe that it's a bit difficult for industry to get their teeth into anything concrete. So that I think it's an ideal area of research for university, trying to look for additional materials for photovoltaics that have some of the excellent properties of silicon, but a different band gap is the big problem. But there are a lot of smaller issues that come up in photovoltaics. So there's endless problems that the industry needs to solve to continue making improvements, and they will be solved, but universities can get involved at all different levels of problem solution with the industry, because it's a very young industry. Despite the fact that it's done so well, it's still a very young industry, and there's going to be a lot of change in it before it reaches its full maturity. So a lot of new technology to be developed along the way. So endless problems to be solved within photovoltaics in its evolutionary path.
Okay, very great. I have to add in one sentence here. As because tomorrow is our soft electronics, competitions for the doctor degrees. So I think I have to mention that the soft electronics, soft solar cells is more important. Okay.
Yeah, flexible. Yeah.
Yeah, flexible and soft materials for that. Okay.
Yeah.
Please, Dr. Jagdish. Yeah.
Okay, good. Thank you very much. And first of all, I would like to take this opportunity to thank Professor Martin Green. And despite the fact it's already past midnight for him, it's 12:40 for him in the AM, for joining us and giving such a fascinating talk and sharing his experiences with us and inspiring us. And of course, also Dr. Zhengrong Shi. And again, we thank him despite the fact that he's very busy and running companies and being a professor and then doing many things. And really thank you for really changing the photovoltaics. Both of you really changed the photovoltaics field in terms of science and technology development and also commercialization of the technologies. Both of you have done a fantastic job. And also we want to thank our young and rising star and Dr. Shanyuan Niu for joining us on this panel and then asking inspiring questions as well. Thank you very much. And also I just would like to finish off next week. Yes.
Yeah,
thank you. Next week, we got this Professor Yasuko Arakawa is going to talk about quantum dots from science to applications, and we look forward to seeing you on next Friday at the Beijing time of 8 p.m. Right. Thank you very much, and good night, and good morning to those of you, and bye-bye. Thank you very much.
Bye, everyone.
Thank you.
Okay, bye-bye.
Thank you. Bye-bye. Thanks, Alice.